if you have any question, leave it into chat. If you comment, leave it into chat section. And later we'll keep it for 15 minutes for discussion. So the webinar is for 1.5 hours. We'll keep 15 minutes later for the discussion with Peter and question answer. Peter, thank you so much. Over to you. You are on mute, Peter.
Good day to you all. Thank you so much for attending this. I hope you all get what you need from it. If I share my screen first, just get this all working. Okay. Can you see that okay?
Yes, Peter.
Yes, we do.
Okay, cool.
Yes.
Right, today I'm going to be talking about risk reduction, mainly about noise control technology, but also there are a couple of other things I think there's been recent research and so on that makes it even more urgent than before. As far as noise risk reduction is concerned, I've been doing this for a very, very long time, and one of the very disappointing things is how little has changed in the last 30 or 40 years. And it's about time people change their risk reduction strategies to best practice. We run lots of training courses for the Institute of Occupational Safety and Health and competency courses and so on in noise, and we see the reports that are issued. We do joint workshops with the Health and Safety Executive in the UK. The general standard is not very good. So what I'm going to be doing today is I'm going to be talking about 4 of the elephants in the room as far as risk reduction is concerned. There's a phrase, don't mention the elephant in the room. It's a very obvious thing, but no one mentions it because it's embarrassing. So I'm going to be talking about the 4 elephants in the room of noise risk reduction, but mainly about noise control. So current risk reduction practices worldwide have failed. There's still millions of people getting hearing damage. In the UK, there's a tsunami of hearing damage claims. And this is all despite the fact that noise-induced hearing loss is 100% preventable. And the reason that people are still going deaf is because people aren't implementing best practice and making sure that people are actually protecting themselves. Recent research has really made this more urgent in the fact that, for example, over the last few years, there has been a lot of research on the links between dementia and hearing loss. Mild hearing loss doubles your chance of developing dementia. For moderate hearing loss, it's a factor of 3. And if you have severe hearing loss, you're 5 times more likely to develop dementia. Noise-induced hearing loss or hearing loss is the single most modifiable risk factor in you developing dementia. It's very close to my heart. My mother is dying of dementia at the moment. It's just one of those factors that your hearing is such an important part of your brain activity. When you lose it, you are likely to get dementia. So this is absolutely a massive thing that people don't normally consider. People normally just talk about hearing loss, but this is another factor that is extremely influenced by any noise-induced hearing loss. In addition to that, in the UK, the statistics for other factors involved in hearing loss, for example, if you have significant hearing loss, you are 42% more likely to be unemployed, 8% more likelihood of early retirement, and you double your likelihood of having a significant accident. So these are all, if you like, outside of the normal consideration of hearing damage. People just say, oh, you're losing your hearing, you get speech is more difficult to understand, you get tinnitus and so on. But these are other factors that also affect your life. So these are very serious things. So noise exposure is costly in terms of health. It's also costly in terms of money and company expenditure on resources to reduce risks. So the costs to operators and staff, noise-induced hearing loss, tinnitus, dementia, and the other things I've talked about. Direct costs, so financial costs, the cost of PPE. So the direct costs of PPE and the indirect costs. In other words, how much attenuation do you actually get from your PPE? There are also costs involved in audiometry in most countries, in that you have to carry out audiometry. Unfortunately, traditional audiometry is not a useful risk reduction exercise. It's a checkbox exercise. Motivationally, perhaps it's useful, but not otherwise, not using conventional audiometry. There are also the massive hassles associated with noise, risk management, policing, claims, organizing audiometry, and so on. There's also the personnel involved. High noise levels make working conditions worse and make communication more difficult. In addition, there's also the fact of risk assessments, the ongoing costs of getting reports. And unfortunately, the noise industry is predicated on measurement. And fundamentally, a lot of organizations get regular noise reports that just tell them what they already know. You still have a problem. It's more difficult to tackle those problems. So looking at the 4 key elephants in the room that people get wrong or don't discuss. Risk assessments for a start. That's the preliminary thing. How risky is it? Why do we keep repeating risk assessments and repeat risk assessments and repeat risk assessments? Most risk assessments are very poor quality placebo exercises. In the UK, HSE research says that most noise reports are inadequate, which is politically polite, saying that they're not at all good. We see a massive number of reports because of the training courses we run, and I completely agree with the HSE. The standard reporting is terrible. Hearing protection. This is the first aid measure that is always introduced. And most hearing protection, hearing conservation programs are based on the use of hearing protection. And there are huge assumptions that are just wrong. So people suffer unnecessary damage without knowing it because they assume they're protected sufficiently. Noise control is an enormous factor because most people assume it's not practical, because the knowledge of modern low-cost noise control engineering is frankly abysmal. As an engineer, I find it really, really depressing. So I'll be talking about that mainly today. And audiometry, if I mentioned that, it's largely a placebo checkbox exercise, but it doesn't have to be. It can be made useful, and there's newish technology now available that really helps on that in that. Now, if you get all these things right, you can reduce the risks of hearing damage by 80 or 90% or more with no increased expenditure. It's just a question of doing the right things. So starting off with risk assessments, this, if you like, is an index of one of our comprehensive risk assessments, where a company really, really wants to start from scratch and get everything down. The bit that's missing in virtually all risk assessments is a noise control audit. You just don't get any information at all about noise control other than copy and pasted stuff from the internet. So I'll be talking about that mainly today. One of the things you do need to do for risk assessments is what we have at the front of the assessment is a 1 to 2 page document, which is the action plan. The only reason you're carrying out a risk assessment is to work out what do you need to do to reduce the risks. So the action plan we pull out, which you can put on someone's desk. This is what you should be doing. It's simple. It's not scary. You don't have to read much, but we have links to the page number and we have the due date, who should be doing it, and when it's completed. So you're keeping track of what actions are taken. In addition, most risk reports are just not useful documents. They're written perhaps for people who like to show how much they know about noise, rather from a manager who knows nothing about noise. They just want to know what they're going to do. So this is a video extract from showing one of our risk assessment reports. Basically, for a factory, it's based on the factory plan. So what we have is a PDF document which has got all the information you need on. It's got noise levels, it's got their color coded. So if it's red, it means the noise dose is above 85 and hearing protection is compulsory. There are also pictures to remind people of which pieces of kit should be is there. And you can also have sound samples. And comments, in this case, this line is particularly noisy, but also noise control. So in this particular case, this conveyor, the noise can be reduced by 12 dBA at about cost of £200, and it reduces the wear in the conveyor. So this is a document, but the document is designed for the engineer implementing the noise control measures. So there is a comment section here. There's also material suppliers. So when they're doing it, you can capture their expertise of how they fix the problem in notes from the engineer. So when that engineer moves job or leaves, follow-on engineers can copy what they did on other items of plant and learn from what's been done in the past. It's turning it into a useful document. As far as PPE is concerned, these graphs are 1996. So this is a long time ago. This is nearly 30 years ago. This knowledge has been available for all that length of time, but virtually nobody makes use of it or even really understands it. So the top one is earplugs. In yellow, we have the manufacturer's data, attenuation, between about 15 and about nearly 30 dB. In red is what you actually get when you measure it, and that's as low as 2 to 3 dB. So basically for these earplugs, you're talking about between 2 dB and around 10 dB if you're lucky. For earmuffs, the situation is slightly better, but it's still around about 10 to 15 dB maximum, no matter what the manufacturer says. This is something that people don't discuss. The manufacturers they know this, but they don't make it general knowledge. So it's a very serious issue that if you need 20 dB or 15 dB attenuation, you're only getting 2 to 5 dB in practice. This is a very serious thing. So if we look at that, why doesn't it work? With earplugs, they're rarely fitted correctly because you need to put them fully into the ears rather than having them dangling out of your ear like a cigarette end. So 20 to 30 dB potentially from the manufacturer, poorly fitted, as low as 2 dB. Earmuffs, there's less variation because it's easier to fit them correctly, but you can only really get 10 to 17 dB hearing protection, no matter what protector you use in practice. The other thing is wear rate. This is one of the really key elephants in the rooms because it should be 100% in a noise hazard zone, but it almost never is. And unless you know what the wear rate is, not what you assume it is, you have no idea of protection you're getting. So these plots here, this is, if you like, showing you the sort of noise level. From the manufacturer's data for plugs, you're expecting 15 to 30 dB, and what you're getting is between 2 and about 12 dB. For earmuffs, you're expecting 20 to 30 dB, and what you're getting is about 5 to 15, 16, 17 dB. So what this means in practical terms is up to 90 dBA, hearing protection is potentially achievable with reasonable enforcement. Between 90 and 95 dB, it is difficult. It is hard to guarantee adequate protection. Above 95 dBA, it's very hard, and above 100 dBA, it's virtually impossible. Not many people know this or really understand this or apply this information. And one of the killers is the wear rate. This graph shows the attenuation you get. Along the x-axis, we have the number of hours in an 8-hour shift that you wear your hearing protection. So in practice, you're only ever going to get around 99% wear rate, which means for plugs, the maximum performance you can ever get is 10 dB, and for muffs, it's 17 dB. If you take them off for 2 hours in your 8-hour shift, or you're just wearing for 3/4 of the time in noise exposure, the maximum attenuation you can get is 5 or 6 dB. Doesn't matter what you're wearing. The wear rate determines your protection. Now, pure tone audiometry is, if you like, the gold standard that everyone uses. The trouble is, it's a simply catalogues you've messed up, that the fact that people have had hearing damage 5, 10, 15 years down the road. So all you can do with conventional audiometry is say, oh, I'm sorry, you've had hearing damage over the last 10 years. It's too late to correct that, but sorry about that. It's a lagging indicator. So it makes it, as far as risk reduction is concerned, it's a placebo checkbox exercise. It is useful in terms of motivation in that you take someone aside every couple of years or so and talk to them about their hearing. But the results are that it will not pick up the early stages. So if you like, all you're doing is documenting the fact that someone has hearing damage or doesn't have hearing damage. In the UK, the HSE have said that conventional audiometry is a tax on the failure to control risk. It is not a risk management tool. It doesn't have to be. There's pure tone, or instead of pure tone audiometry, we recommend, if you can, investigating otoacoustic emission. This has been used to test the hearing of children for decades. Now there's an industrial version, which has been around for a few years. And the advantages are, if we're comparing pure tone audiometry, the conventional audiometry with OAE, OAE detects the very early stages. So you can say last year you had 12% damage to your hair cells, this year you have 18%. So you know something is going wrong within a year. So you can then say, what has gone wrong? You're not wearing your hearing protection, or we haven't picked up a risk that you're from where you're getting damage, and you can do something about it. So it becomes a risk management tool. It's also very, very easily understood. It's percentage damage. It's very good for motivation because it's urgent. You know, you have got this much damage since last year. It's also objective. There's no subjectivity about it. So you don't need to participate. You don't need to tell people what they need to do. You just press a button and it gives you the answer. You don't need quiet booths. It can be done in a quiet office, and it complies with all regulatory health surveillance requirements, as does conventional audiometry, technically speaking, but not in reality. And now we come to noise control. Now, where you have a 3 dB rule, double the energy is double the risk, because risk is directly proportional to energy, noise energy. So if you have a 3 dB exchange rate, which is the most common generally accepted one, risk is directly proportional to the total amount of energy entering your ears. 3 decibels is double the energy, so that's a 50% increase or risk reduction, increase or reduction in risk. Every time you add 3 dB, you're doubling the risk. So 3 dB increase in noise level is a 50% increased risk or a 50% reduction. So if you're looking at noise control, one of the problems you've got is that quite often people will say, well, it's 100 dBA. There's no point doing anything if I can't get it below 85, because at 85, we don't have to wear hearing protection. At 100 dBA, I can tell you those people are not adequately protected. So if you can reduce it from 100 down to 97, you have halved the risk. If you can reduce it from 100 down to 94, 6 dB reduction, you have reduced the risk by 75%. And a 10 dB noise reduction means you have reduced the risk by 90%. So if you can get it down from 100 dBA to 90 dBA, hearing protection is still mandatory, but it works. People can be protected at that level, whereas they cannot be protected at 100 dBA. And the assumption is that noise control is really going to be very, very expensive, and that's not true. General knowledge of modern low-cost engineering noise control techniques is seriously abysmal. It is so bad. And as health professionals, occupational hygiene professionals, you know this, that hierarchy control. So the hierarchy control is touted as the first thing you do is to cut the risk. And for noise control, it should be noise control, because that eliminates the risk or reduces the risk. And then substitution, and then separation, and then admin, and then PPE as a last resort. For noise, it's the opposite way up. What happens is noise assessment reports will say, always, first thing you do is PPE. Fair enough as first aid, but that's it. No one considers the other measures in any great seriousness in most circumstances. This is a big problem because, as I've said, PPE is not nearly as effective as people think in practice. And the problem is attitude to noise control. And a typical discussion you get in health and safety across the world is, let's look at noise. Noise has become a topic because you had a hearing damage claim, or it's just come to the top of the pile. So let's look at noise control. At the meeting, we've had quotes for enclosures, and they're exorbitant, they're massive costs, and the maintenance engineers would hate them, and hygiene would be a big issue, and so on. So it's not going to be practical. Moving on. There's a tendency to regard noise control as a safety issue. It's not a safety issue. Identifying the risk is a safety issue. As soon as you've done that, it becomes an engineering problem that should be addressed by engineering means. And that means accurate diagnosis. Again, virtually everybody involved in noise will look at a machine or a noisy line and go, it's like a black box. That's it. They don't look at it as an engineer and say, why is it noisy? And that's the key thing. So for noise control to be effective, you must look at all the options, not just the high cost conventional palliatives such enclosures and barriers and silencers. And you should only use those palliatives when you can prove there's no engineering alternative. And all these techniques are additive. This picture highlights the problem. This is an environmental noise problem, but it's a grain dryer on a hill in the countryside. So 9 fans, it's like an organ, and for everyone for miles around complained. So the manufacturer came to us and said, look, we gather you have this clever noise control technique because it's installed and fitting silencers would be a nightmare. So we designed aerodynamic inserts to fit inside the fans, which cured the problem. But the farmer wouldn't pay because he had in his head, where are the silencers? He had this sort of idea that somewhere behind the machine is a switch that goes noisy, quiet, noisy, quiet. How can you make a machine quiet with a fan quiet without fitting silencers? So these orange boxes here are called Helmholtz resonator silencers, they are placebo silencers fitted to get paid. They did knock another 4 dB off, but that's completely unnecessary. It's this attitude that you have to add stuff, you have to add in silencers, you have to add enclosures, you have to add barriers to reduce noise. They are fallback if you can't get rid of the noise by engineering means. So to evaluate what your noise control options are, you need to carry out a noise control audit, which is a cost-benefit analysis. So this is taken from a previous project. So there's a site with scrap fans pulling things off the lines, pulling scrap off the lines. They're crowding conveyors, they're filling machines, sorter capping machines, cartoners, and palletizing. Current noise levels shown here, pretty high, up to 98 dBA. And one of our engineers went on the site and did diagnostic measurements and worked out what the noise control options are and what the cost would be. So to get the noise level down from 98 to 76 cost about £3,500 and so on. So in each case, we're saying these are the predicted noise levels you can achieve for these costs. And if you add all that together, you can say the total cost of the noise control program, which would then give you a maximum noise level of 83, down from 98, and the estimated annual maintenance costs are around £3,000, but you'd be saving £1,000 on compressed air. So then you know what the cost is going to be, and you know what the benefit is going to be. And in this particular case, when you worked out the noise dose of the people working in these areas, all the noise doses were well below 85 and most were well below 80. So in most areas, hearing protection would no longer be required at all. You then look at the real costs of PPE. So the first thing we do is we have a real world PPE performance calculator. So in this case, you put in the type of muffs. These are ear muffs. The manufacturer's data says 24 dB. The wear rate we've seen is 70%. They're wearing safety glasses. They've had fit testing. The cost per head per annum is £180. And the number of staff is 50 wearing them. So the total capital cost per annum is £9,000. But you're only getting about 5 dBA noise reduction. So you say, okay, I'm spending £9,000 a year and I'm only getting 5 dB. And if you put that cost figure, and then you add in the other costs such as noise surveys per annum, audiometry per annum, admin per annum, insurance per annum, the increased insurance cost because you've got noise problems, any claims, and staff turnover and absentees, you can sort of put in some notional figures for that, and it comes out to around £15,500 per year. So you've worked out the cost of the noise control. You've worked out the cost of PPE and the benefits of PPE, and you can then plot this on a graph. So this graph, these are years, and this is cost. So what we have is the noise control cost is in blue with the maintenance costs adding to it. So the green line is the cost of having a noise control program implemented over the next 6 years. And that means no mandatory hearing protection anywhere. And then you do the same for the PPE costs, which tell you that the red line here. And you can see the crossover point is about 2.5 years. So that means that after 2.5 years, you're going to be saving money by going down the noise control route. You also have to bear in mind that these PPE costs are for about 5 dB attenuation as found. So that would need to be improved. So you have to spend considerably more money and time and energy to improve that. So that's what you're trying to do. You're trying to say, what are my noise control options and what would the cost be? With that information, you can make a judgment about spending money on PPE and noise control or a mixture of both. What is the best option to reduce the risk to a minimum? Now, as far as knowledge of noise control is concerned, a few things that most people don't know. That you can cut fan noise at source without using silencers by increasing fan efficiency. That's our first step when we are tackling fan noise problems. There are also new materials. There's metamaterial barriers, which are amazing devices, which are 25% open area. They use geometric noise cancellations to stop the noise. So you can get 10 or 20 dB attenuation, but you're allowing 25% of the air through, 25% open area, so you can get cooling. On noise, in terms of air noise, silencing and nozzles, you can, in particular nozzles used for transport of materials and so on, you can reduce the noise by 90% and use 20% less compressed air. So it's actually profitable. You do it even if noise wasn't an issue. You can also get waterproof and very hygienic acoustic absorbent now. So that's no longer a problem. And there's also, as an engineer, I really love this material, which is sound damp steel laminate. Looks like steel, sounds like rubber. I love it because it's very robust. You can swap, it's a direct swap for a conventional steel sheet, or you can create it in situ. And here's an example of using a piece of sound damp steel against the deflector already in use on this machine. So all engineers should know about this stuff. It's only been around for 40 or 50 years, and it is used in automotive engineering quite a lot. Another one that I think this is really cool, maybe I should get out much, but this is quiet sellotape, quiet tape. On packaging and cartoning, you think, why is tape noisy? Well, if you're cartoning and putting large strips of tape off a line, you can generate 100 dBA locally. Quite often, people are looking at fitting enclosures. Why not buy quiet tape?
Okay.
Maybe I'm just very sad, but I think that's brilliant. Also, when I set up INVC decades ago, we bought a narrowband frequency analyzer for diagnostic purposes. It cost the same as a small car. Now you can do it on a free app on your phone. So where you have a lot of noise is tonal, and the tones, the peaks in the noise at different frequencies, can be related to mechanical activities such as gear mesh, such as fan blade pass frequencies and so on, and structural resonances. On a free app, you can determine what is causing that tone, what is causing that noise. And we use this for diagnostic purposes all around the world. We do a massive number of projects now across the globe from our offices in Slough, just by analyzing smartphone data, or in this case, from a TV program.
Some homeowners who live near Mission Hospital say they're fed up with a constant humming. They also say Mission leaders aren't doing enough to fix it.
News 13's Kimberly King talked with neighbors who are filing a complaint with the city.
Listen closely. Can you hear a constant hum? It's a sound residents say is coming from Mission Hospital, not.
From that sound sample, I did the analysis, the frequency analysis, and said, well, the problem is these two peaks here. I contacted them and they had, I predicted that it would be 8-bladed fans, 2 of them running at a certain speed, and they had spent a lot of time and money on the wrong piece of kit because they hadn't done the diagnosis. So it wasn't these chillers, it was these chillers. So that diagnostic, me spending 10 minutes analyzing that, told me exactly what the noise source was. This is another example. This is the fastest noise control project we've ever done. Took 6 hours from the first phone call to the problem being completely diagnosed and them knowing exactly what they needed to do. This is a cooling tower. They sent me a video clip from the analysis, close to the tower at a distance. The problem is a tone at about 650 hertz, which was tied into the gearbox of the cooling tower. So once that had been done, instead of spending over £30,000 on replacing the whole unit, they just needed to replace a gear, which cost them £3,000. And that was all completed within 6 hours from the first contact. This is incredibly powerful diagnostic technique. So as far as diagnosis is concerned, it's a way of thinking. You look at your noise sources and you say, why is it noisy? So the things you can do, and you need to rank the noise sources on your machine or on your line or on your plant. So listening, does the noise happen at the end of the cycle, the beginning of the cycle? Is there a hum? Is there a whine? Is there a drone? If you're an engineer, a lot of engineers have used this for years. You know, you've got a problem on a gearbox or an engine, and you stick a screwdriver in your ear and listen to it. And you go, ah, right, okay, is that bearing? Or you can run each source separately. So on some machines, when you press the start button, the fan starts up, the motor starts up, and various other things all start at once. So if you can get an electrician to massage the interlocks and try and run each bit separately. So you run the motor and gearbox, and then separately you run the compressed air separately, and you then run the extract fan separately. And you can say, right, which is the noisiest? Because the key thing is you start with the noisiest noise source and work down the list. Otherwise, you're not going to be successful. Another thing you can do is you can buy acoustic matting and cover all the sources. So this is a bit like a children's program where you make, with a pair of scissors and a Stanley knife, you make covers for each noise source, and then you cover them all, and then you uncover each one in turn. And that tells you simply which is the noisiest part of the machine. If you have tonal noise, you can use an app on your smartphone to do narrowband frequency analysis and correlate that with mechanical components. Is it gear mesh? Is it rotational speed? Is it fan blade pass, and so on? So those are very easy to do, and anybody can do those. More difficult is to measure close in and calculate the predict the noise level from close in microphone measurements. You just need a very simple sound level meter and a calculator. Or what we do quite often is to measure the surface vibration velocity and then calculate the contribution from that particular noise source. The power of this is illustrated by what would normally be considered a very difficult noise problem. So this is a big power press. You've probably all lain awake at night wondering if you've got a washing machine and you look inside your washing machine and there's a perforated drum, stainless steel perforated drum. You've probably lain awake at night wondering what machine puts all the holes in the stainless steel they make the drum from. Or maybe that's just me again. So this is a machine that does exactly that. You feed in the stainless steel sheet and it stamps out the holes. Now, this machine is generating 102 dBA, which means the whole of the area with a load of staff are all affected by the noise, not just the operator, and all have to wear hearing protection all the time. Now, the company were thinking fitting an enclosure, which would have cost tens of thousands of pounds. And they asked us to see if there's an alternative, because it would have been a big hassle and very difficult to operate with an enclosure around it for access and so on. So the first thing to do is work out make a list of the noise sources. So we have the tooling banging away. We also have a clutch, a pneumatic clutch that is operating the tool as well. You also have an extract fan, which is pulling out the scrap, and we have a separator that pulls out the scrap from the outlet of the fan. So the first thing to do, run the press without the feed going through it. You can run everything else, and that we did that, and that's by far the dominant noise source. So we tackle that first. So with tooling modifications, which is really just regrinding the tool and modifying the tool slightly, we're down from 102 to 97 dBA. A good start. But then the clutch is the dominant noise source. It's compressed air from this very bad silencer. So fitting a much better silencer, straight through silencer, so no back pressure at all. Fixing that, we're down to 95. Then the fan is the dominant noise source. So an aerodynamic modification fitted to that, so the scrap could still go through it without damage, down to 92. And then the cyclone, which separates out the scrap, modify that, we're down to 90. And silencing the outfeed, we're down to 87. So we're down from 102 to 87 dBA, which means you only need to wear hearing protection compulsorily within 2 meters of the press. The rest of the workshop is no longer a mandatory hearing protection area. And that lot cost a tiny, tiny fraction of an enclosure. Instead of spending 40 or 50,000 pounds, it cost them about 5,000 pounds. Now, something else you can do using this equation, I will be providing a PDF of this PowerPoint presentation, so you can look this up and use it yourselves. So you have noise coming out of the fan. Off the fan casing, this is the fan casing here, and off the fan mount and off the motor that's driving the fan. So how do you know how much is coming off each? Whether it's the motor fan, cooling fan of the motor, all these components. So what you do is you scan, you set your meter to measure the average noise level, and you just scan across this surface. So you get the average noise level of number 1, and you know the area. So number 1, the average noise level from the microphone held very close to the surface is 85, and the area is 1 square meter. So you put this into the equation, 85 plus 10 log 1 is 85. Area 2, the average noise level is 91, and it's 0.6 square meters. So you put it into the equation and it comes out to 89 is the total sound energy radiated. Area 3 is 89, is 0.2 square meters. So the average total energy is 82. And the fan on the back is 98. It's tiny, 0.1 square meters, but it's noisy. And that comes to 88. So you can then rank all these noise sources. You can rank them. So the noisiest bit is number 2. Second noisiest bit is the cooling fan on the motor. The third noisiest bit is the fan casing, and the fourth noisiest bit is this end panel here. So this enables you to rank the various noise radiated from the various surfaces quite quickly and easily. So we're looking at using modern engineering noise control techniques, 50 to 90% cost savings. So typically it will cost half as much or 10% as much as using conventional noise control. So pneumatic noise, you have 0 back pressure silencers. Pneumatic noise, there is no excuse for pneumatic noise from exhaust from silencers. And I'll come to that in more detail a bit later on. If you're using nozzles, there are off-the-shelf nozzles that use 20% less compressed air and are 10 dB quieter or even more. Weighing with hoppers, chutes and conveyors, we have impacts of products and so on. You can get 10 to 30 dB attenuation using damping. No effect on maintenance, no effect on hygiene, very, very cheap. Silencers, you can do a lot without silencers, and if you need, by increasing efficiency and so on. And if you need silencers, there are various types of silencer. You can convert existing parts of the system into silencing components. Large power presses, I've already shown one example. I can show you another example in a moment. Vibratory feeders, very, very common, between 5 and 27 dB attenuation with improved performance. So you're getting improved throughput. And typical cost once you've done the first one may be just a few £100. And construction plant, simple mobile screens. You can knock the noise by 90% by 10 dB or more by fitting mobile screens. So let's look at some of the things. This is available on our website in more detail. You can download the document, but I'm going to go through some of these these are typical noise control solutions to very, very common noise problems across industry. These are the 10 most common noise control problems and the best solutions. So first off, any thin steel panel that is vibrating will radiate that vibration as noise. Now you can stick rubber type material, damping material on to damp it, but that will come off. It's not hygienic and it's not rugged. You can buy off the shelf laminated steel, laminated aluminium, laminated stainless steel. I love it. It's cheap. It's very robust. And it's also high hygiene. You can also create a laminate in situ. So you can laminate an existing panel by using high damping adhesive and just sticking another sheet of steel onto it. So this is very cheap and very, very effective. An example of that in use is weighing machines in the food industry. So this is a weighing machine, and underneath you have the bagging machine. So you're weighing out set amounts of sweets or pharmaceutical products into containers. On the platform, without the enclosure, it's 94 dBA for the weighing machines. Sorry, 94 dBA with the enclosure. This is a very sophisticated enclosure, and yet it's still 94 dBA. Underneath the enclosure, it's actually louder with the enclosure than without the enclosure, because the enclosure is funneling the noise down to where the operator stands underneath. Now, we have a standard fix for this, which involves the laminated steel and a couple of other minor modifications, geometric modifications. So in this particular case, with the enclosure, it's 94 dBA. With our modifications installed, which is mainly damping and a couple of geometry changes, we're down to 82. So PP is unnecessary, and throughput is improved because you've got better access, better cleaning, and easier maintenance. So across all weighing machines, typically they generate 87 to 98 dBA, and hygiene is often an issue. Enclosures typically give about 5 dBA off, and it increases the operator noise level underneath, and it gives you all the maintenance and access problems. Cost £8,000 for a simple one, up to as much as you want to pay. Now, the manufacturers of weighing machines know what we do, but they make more money out of selling enclosures, so they won't do it. So we're talking about less than 50% of the cost. It may be between 10 and 50% of the cost, depending on the sophistication, and 4 times performance for an enclosure. So why wouldn't you? And this is what it sounds like. So that's 12 dBA quieter. This is a power station. These are big water pumps, very, very noisy close in, 95 dBA at a meter. Big argument between the supplier of the pump and the supplier of the motor. It's your fault. No, it's your fault. No, it's your fault. So we were asked to look at it, and we got the data together. Again, this was done remotely over the internet. Got them to do some simple measurements and send a couple of smartphone video recordings through. 100 hertz tooth comb, which means electrical vibration, which is being radiated by the thin metal panels on this big pump. So the thin metal panels were laminated, and 12 dBA noise reduction, very, very cheap, was done over a weekend. You've probably wondered what makes the oil filter base plate on your car, for the oil filter on your car. It's a thick piece of steel stamped with holes through it. It's a large press. The manufacturer using that press was going to fit an enclosure, again costing about £35,000, but access is an issue. So we looked at it and found that most of the noise is radiated by the flywheel. The flywheel is acting like a loudspeaker, ringing like a bell. So what we did was, in London, there's the Millennium Bridge, which is a beautiful structure. But when people walked over it when they first opened it, they all started to walk in step, because the bridge started to sway at about 2 cycles, which is about walking pace. And so it swayed from side to side and was quite scary for the people walking across it. So as soon as I heard about that, I thought dynamic vibration absorbers. These are a mass on a spring with a damper. what it does is it sucks out the vibration at a particular frequency and converts it into heat. And it's very, very efficient. And they did that to the bridge. I think they should have not modified it. They should have charged it for it as a ride. But anyway, they fitted dynamic vibration absorbers, which cured the problem. On the flywheel, we did some tap tests, worked out where to fit the absorbers. An absorber is just a lump of steel on a piece of cork, which has got the right thickness and the right area, bolted through the flanges of the flywheel. That gave a 10 dBA noise reduction and cost £20 in materials and a fitter for a day, and sounded like this. And that was all done inside the original guards. Vibration isolation is where you're preventing the transmission of vibration from something that vibrates a lot into something that radiates the noise. So this is a water pump, quite noisy, because the pump and the motor are bolted to this steel structure to give you the alignment. Now, if you suspend the motor pump unit in free space, they're actually quite quiet. But because you've bolted them to this big piece of steel, it acts like a loudspeaker. So if you could isolate the motor pump unit, what you do is you buy in something like TecoPad. There's various manufacturers of this. This is rubber bonded cork gasket material of various thicknesses. We quite often see this used, and people will proudly point to their pump or their gearbox and say that's vibration isolated from the beam that's radiating the noise. And they've done this. So here's the isolation pad, but you're bolting straight through it. So what's happening is the vibration is going through the bolt. You may as well not have bothered. You've just jacked up the amount, the foot of the machine by a few millimeters. You need to isolate under the head of the bolt. So this one is isolated. It's very cheap, very, very simple. Takes out high frequencies and can reduce noise by 10 to 20 dB. Axial fan installations, fans are a very, very common source of noise, both environmentally and occupationally. And noise is turbulence in the air. So what you're trying to do for axial fan installations, here we see we use computer fluid dynamics to work out what sort of turbulence you've got to make the fan as efficient as possible. We modify the aerodynamics. So in this particular case, there is an example of this, is that where you have a blunt end opening, you get turbulence being fed into the fan. So you fit a bell mouth, which gives you smooth flow into the fan. In one case, 6 dBA noise reduction, and the fan is more efficient because it's running in cleaner air, less turbulent air. If you have any obstructions in the duct, it can be things like vibration breaks. So if they are impinging inside the duct, they will cause turbulence. If you have a damper, that will cause turbulence. So what you need to do as a rule of thumb is you need to have 2 to 3 duct diameters of straight, smooth duct between anything that causes turbulence and the fan. This will reduce the noise dramatically. Or you can buy in quiet fan blades. They're more expensive and they do help to some extent, not massively, but they do help. The way we approach any fan noise problem is to try and make the system as efficient as possible. And the reason that's so important is because nowadays you can get variable speed drives quite cheaply. You can also, if you've got pulley driven fans, you can just change the size of the pulleys to change the speed. And the reason that's important is because fan noise is proportional to approximately the 5th power of fan speed. And what that means is that a small reduction in fan speed has a big effect on noise. So if you cut the speed by 10%, you reduce the noise by 2 dB. If you can cut the fan speed by 20%, you reduce the noise by 5 dB. That's a factor of 3. So cutting the noise from a fan by 5 dB means you've reduced the noise risk by a factor of 3. You're down to 1/3 of the risk, and you've got a 20% reduction in fan speed and reduced power consumption. And you can see a 50% reduction in fan speed in your dreams. You get 15 dB off, which is a factor of 30. So the first thing we try to do is to say, what can we do to improve the efficiency of the fan system to reduce the noise? The next thing we do is say, okay, can we introduce aerodynamic fan noise control? Because this cuts the fan noise at source. We originally developed that for the Eurofighter project as a small fan in the ejector seat that fed the pilot, and they couldn't use silencers. So we developed aerodynamic inserts that fit inside the fan casing to cut the noise. And it can also increase efficiency in some cases as well. So where that's applicable, it's very, very cost effective. It's very cheap, easily retrofitted, and can give you efficiency improvements. If you can't do that, then you fall back to the conventional silencing, enclosures, lagging barriers, and building modifications. To give you an idea of some of the past projects, this is a scrap fan, which is pulling aluminium cans off the line. So when you get a duff can, a faulty can, you pull this scrap aluminium can off the lines, and it's fed through these chopper fans, which shred it, and that aluminium is then recycled. Now, it was both an occupational and an environmental noise problem, 3 systems. They were quoted £35,000 per system for silencers, lagging, and enclosures. It has to be very, very robust silencers because aluminium cans are passing through the silencers. We fitted aerodynamic noise control, which cut the noise by 22 dBA and cost £3,000 per system rather than £35,000. And it sounded like this. So where it's applicable, phenomenally cost effective. This is a manufacturer who had an occupational noise problem. A dust control fan is used in factories where you have a lot of dust. You don't want to get the buildup of dust because it's an explosive risk. So they have these fans that are hung from joists. Very noisy. It was 87 dBA at ground level below the fans. And they wanted to reduce the noise. So we redesigned the aerodynamics of the fan, which cut the tonal noise, the hum, which is very annoying, by 98%. It cut the overall noise level by 75%, reducing the occupational noise risk by 75%, by a 6 dBA noise reduction, reduced power consumption, reduced pressure head, increased air velocity by 17% at 12 meters, which is where you need it to cut the dust. So you can see from this picture and the way it sounds. The key thing is engineering noise control. If you do the diagnosis and you can do good engineering, there's the potential for a very low cost solution that also can save money and makes things more efficient. It should always be the first port of call. I particularly like this one because it uses yogurt. And I don't know if any other noise controllers ever use yogurt. A colleague of mine was asked to look at these boilers, which are a noise problem, low frequency noise problem. They were going to turn the boiler house into a bunker because a lot of complaints. He looked at the burner and said, I don't think the flame is stable. So he said, have you got a yogurt pot? So they went to the canteen, ate a yogurt, and he came out and he modified a yogurt pot. They fitted it and it got rid of the tones, 16 dB off the tones, just by fitting a yogurt pot. They do have aluminium yogurt pots now, and the noise, you probably can't hear this because it's low frequency, and I don't know how good your headphones are. So these things are now run with aluminium yogurt pots, and before you ask, it was blackcurrant. Pneumatic noise, incredibly common. Unsilenced exhausts, maybe 100 to 110 or even more, 115 dBA. So that means 1 second at 2 meters from an exhaust is all you need per day to get your full dose. 1 second. There are dozens and dozens and dozens of silencers available. Most of them are terrible. And one of the problems with silencers is, unless your air is very, very clean, they will eventually clog. So they will get removed, and that means that you've got the noise back. So you can get zero back pressure silencers. So back pressure is not a problem. It's often a rumor you can't have silencers on this machine because of the back pressure. So these are the practicalities. If a silencer is missing and there's 75 different silencers on your books, it's a hassle, and the machine still runs fine with no silencer. So what we tend to do is we say, okay, the difference between having an effective silencing program and an ineffective one is you should standardize all your exhaust ports to 3 sizes and stock 3 silencers, big, small, and medium-sized. So you can, whenever there's a problem, you just replace the silencer. Very, very easy. And as I said, 0 back pressure. If you have a lot of exhausts, in this case, we recommended they feed them all into one pipe, which is connected to the rear box of a car silencer. So you go down your local car silencer shop and buy the rear box. That will knock the exhaust noise by 35 to 40 dB and is very cheap and simple. So these are all manifolded into straight through silencers with 0 back pressure. If you're using nozzles for cooling, drying, conveying materials, knocking things off, whatever, standard nozzles, usually just copper pipes or something similar. You can buy what are called entraining nozzles like these. They are about 10 dB quieter, is only a 90% reduction in risk for the same thrust. They use 20% less compressed air, so they pay for themselves very quickly and they're intrinsically safe. It's a no-brainer. Here's an example used on toothpaste manufacturing. These 2 tubes are used to cool the plastic welding on the ends of the tubes. So the tubes stand upright in these cups and it passes between these 2 to cool the welds. Very noisy. 94, they'll go to fit an enclosure. We designed entraining nozzles which knock the noise by 12 dB and use 20% less compressed air. Again, it's looking at a noise problem in a way that says, why is it noisy, and trying to fix that. These things are available ex stock, off the shelf. Another common noise source are chains and timing belts. Timing belts, with chains, they usually get loose, and so the return feed may be noisy. So you can fix that with laminated steel guides so that it's not rattling against guards and things. With tooth belts, the noise is caused by the expulsion of air from between the teeth. You can buy quiet tooth profiles, and you can buy chevron tooth patterns that are seriously quiet, more expensive, but seriously quiet. Or if you've got a 10 centimeter wide belt, split it into 3 narrow belts, and it'll be much quieter. And the other thing is, these are very sensitive to belt tension. A very small increase in belt tension can double or treble the noise. So what we tend to do is to have instructions on how to measure the belt tension next to the belt, so the fitter, when he's changing the belt, will get it right. These things can cut the noise from belts by between 5 and 20 dB and is virtually no cost. Purchasing policy is another thing. These 2 oil pumps are doing exactly the same job. One of them generates 104 dBA at half a meter, and the other generates 92 dBA. Buy quiet motors. Hydraulic power packs is another very common one. This one here is on a site. Here's an oil tank with submerged pumps hung off the bottom of this motor, with also a cooling air system as well to cool the oil. To try and reduce the noise, they fitted a screen around it. That hides it from leaks. Other organizations have fitted enclosures. I hate the idea of enclosures around pumps, around hydraulic power packs, because you can't see leaks and the temperature inside will rocket. Now, the reason it's noisy is if you take your motor pump unit and suspend it in free space, it's quiet, but then you bolt it to an enormous loudspeaker called an oil tank. And that puts the noise level up by between 10 and 25 dBA. So the trick is, all you need to do is vibration isolate this from the tank using the rubber bonded cork pads and fit flexible connectors. There's no rigid connection between the pump and the tank. If you need to have these aligned, so this is on a frame to keep the alignment. In this particular case, you laminate this frame, and also you replace this coupling guard with a laminated version. And doing that helps. But the other thing you do is then you vibration isolate underneath, and you're talking about 10 to 20 dBA noise reductions, very cheap, and no heat, visibility, or oil leakage problems. The other thing you can do is to improve existing guards. A lot of existing safety guards are not acoustically effective. So the first thing to do, if there are gaps around your guard, around the edges of the guard, at the joints between guards, or because of damage, if you halve the open area of these gaps just by fitting plates or flaps, you knock 3 dB off the noise. If you can reduce the open area by 90%, you reduce the noise radiated by 10 dB. So reducing the gaps has a substantial effect on noise. That's the first thing to do. The second thing to do is to fit acoustic absorbent inside the guards. It doesn't really matter where you fit it. You can fit it on the top or on one side or one edge. The more the better. But quite often you need visibility, so maybe putting it on the top or on the back. Fitting an appreciable area acoustic absorbent will reduce the noise inside by around 5 dB. That means you've got 5 dB less forcing itself out through the cracks in the gaps in the guarding. And so it can be very, very effective in converting existing guards into acoustically effective guards. And if guard vibration is a noise, is a problem, in other words, you've got thin steel guards, laminate them. And also, if you've got gaps, these are mesh guards in front of a press. Turn up, piece of cardboard, measure the noise. How much noise reduction do you get if you cover that open guard and fit some acoustic absorbent behind it? You can just test that with cardboard in 15 minutes and tells you the answer. This graph shows you how much reduction you get depending upon the leaks you have. So this, along the x-axis, is a potential transmission loss, the attenuation provided by the material you've made your guards from. And up here is the transmission loss you actually achieve. So if we take a steel guard or a Perspex or polycarbonate guard, it gives you 30 dB in airborne sound transmission loss. If you fit completely hermetically sealed guards, the noise will reduce by 30 dB. If you have a 10% gap, 10% open area, the maximum attenuation you get is 10 dB. If you have 1% open area, the maximum attenuation you can get is 20 dB. 0.1% open area, the maximum attenuation you can get is 30 dB. So it's very dependent upon the open area. Now we have the benefit of having developed a massive noise control database. And a very useful way of thinking about noise sources is to split them into two categories. Mechanical noise sources, which are caused by vibration. So you have machine guards, you have hoppers, you have impacts, you have weighing machines, chain drives, electric motors, electrical noise, which vibrates, you have gear mesh, etc., etc., etc. You also have aerodynamic noise sources, such as pneumatic exhausts, cooling, conveying, component discharge, fans, and combustion, and so on. These generate the noise which is transmitted through the air into the open space. These are from vibration that's then radiated by mechanical parts of the machine. It's a very useful way of thinking, of helping you work out what the noise sources are and what the options are. So we have made our database online. We have hundreds, we have dozens and dozens of case studies, a couple of hundred case studies on our website. So that's a resource. And at the end of this presentation, there's a list of resources from various organizations which give you options, noise control options. So when we're looking at noise sources around the world from companies and organizations who can either look on we will pass this data through our own database, and it's a free service. So if you send us noise data, noise levels, reports of noise, what noise levels you got, pictures of the items and of each item of noisy part, and a smartphone video clip, we will then analyze it, run it through our database and say, okay, we've got similar examples. There are these technologies. We may have a few questions about operation and maintenance hygiene and so on. And we can probably give you a very good idea of the noise control options. And we can also make one of our engineers available via WhatsApp. So you can have a sort of an engineering expert on your shoulder, on your phone, while you look at some of the plant that's key to what you really want to reduce noise from. So the process is video, sound, photos, information from smartphone to us. We run it through our database and can give you an idea of the noise control options and the sort of costs involved. It's quite useful if you get a quote for something horrendous like a massive enclosure and you're thinking, well, that's going to cause all sorts of problems and it's very expensive. Might there be an alternative option? Take a look at the resources I'm going to show you later on online, or contact us with that. And we do this anywhere in the world. The other thing you need to do is to have a purchasing policy. There's no point making plant quiet if you then buy noisy plant in. And a purchasing policy can be quite simple. We've got some information on our website about this, but the key thing is, if you just say to a supplier, we want to hit 80 dBA, they will sell you an enclosure. And the chances are that's not best practice. So what they'll do is they'll buy in an enclosure, mark it up and sell it on to you. Whether that's best practice or not is they won't know because they don't have the expertise. Don't let your suppliers spend your money on noise control without close scrutiny and without them having proved to you that they've done the diagnosis, so you know what best practice would be. So here are some online resources. And again, these are provided in this presentation, so you'll get a copy of this by email if you attended, and you can then check on some of these. So they're resources from various organizations across the world. So I think the key thing, the key elephants in the room. Let me go back to a previous slide, a summary slide. As far as reducing risk is concerned, are to address oops, I'll get it right in a minute. It's a live show, folks. Sorry about that. There we go. So I touched on risk assessments. They never contain anything about noise control. Try and make them useful. They should provide you with action plan to reduce the risk. Hearing protection. If you're above 90 dBA, you're in trouble. Because in the real world, as measured, you're lucky to get more than 5 to 10 dB attenuation. If you need more than that, you have to be incredibly careful and work very hard at it. There is some new intelligent hearing protection on the market now, which can tell you what the wear rate is and can tell you what the noise level inside the hearing protection is, so you can investigate that as well. It's very new, so it's not generally available. It's available in the UK and a few other places, but not generally yet. Audiometry, I would suggest trying to switch to OAE if you can and if it's available. But noise control, if you can reduce the noise, you can get rid of the problem. Even if you can't reduce it to below 85 or 80 dBA, you can reduce it enough such that hearing protection will work easily. So if you can get down below 90, hearing protection can be made to work quite easily. Above 90, not so much. And noise risk is directly proportional to noise level. So if you can cut the noise from 97 down to 94, hearing protection is still required, but you have halved the risk. So thank you very much for that. Any questions?
Wonderful. Wonderful. What I've heard. One good part is that many a time speakers keeps giving the same presentation, which was given 5 years ago. What Peter does is every presentation, he brings a new ideas, a new controls. For example, enlightening was how much really earplugs are reducing the noise level. All of us have been using either NIOSH or OSHA effective noise reduction rating of minus, 7 dB divided by 3, divided by half. And using that as an effective noise reduction rating, what we are hearing is that actual reduction you get is even less than that. So thank you so much. A question, we have time for the question. You can leave it in the chat section. One question from Daivik is, which application software is used to prepare risk assessment? Are there
Um,
tools available? Yeah.
We use a template that we have for a massive, for the sort of all singing, all dancing one. But I am on a committee that's been developing a sort of checklist for noise reports. Most
Okay.
noise reports are awful, really badly written. There's too much information that's not well presented. All the technical stuff should be in the appendices. What you want is a summary at the front. This is what you need to do this year. This is what you need to do next year. That's why you're doing it. We will be producing a new template, reporting template, which we will make open source sometime in the next few months.
Right.
So you can copy and paste it.
Very nice. Any other questions from anybody else? Right. Good. Provide your feedback also.
The question here, given the issues with
presentation,
PPE,
right.
overhyping its performance, overprotection. Overprotection is an issue because if someone is, if the noise level is, say, a typical food industry, for example, noise level is high 80s, maybe 90 or low 90s. You then put on 20 to 30 dB hearing protection, and while you're wearing it, the noise level inside is down to 70 or less. So people feel isolated. It's also extremely big problem, for example, in workshops such as vehicle maintenance and so on, where you have very intermittent use of tools. So tools may be only used for a total of half an hour a day, but the noise levels are 100 dBA, so you need to wear hearing protection whilst using the tools. If you make the whole area mandatory, people are going to be isolated because the noise is quiet most of the time. Hear-through hearing protection is a very good solution to that because people can hear low noise levels in speech, so they're not overprotected. So it's electronic hearing protection that passes through low noise levels but stops high noise, dangerous noise levels getting through. So there is no easy answer, but you can look at hear-through hearing protection, which is a very good option. It's more expensive though, so you have to weigh up the pros and cons of how you're going to manage the risks against the cost of the hearing protection and so on. Again, it's a very salutary exercise to work out how much you're spending on risk reduction in hearing protection, that list I showed you earlier. We have people on our courses who go away and they come back the next day going, oh my God, I hadn't realized we're spending £10,000 a year and we're only getting 3 dB. We've got to change this. It's not good value. How available is OAE? It's becoming available in the UK and Europe. I'm not sure about the rest of the world. It's only been used for decades for testing babies, but now they have honed the software and it's very simple to use and tells you what percentage damage you've got at a very early stage. And it's a no-brainer for me because it gives you the feedback within a year that you need to do something. In other words, it's a risk reduction tool rather than, oh, I'm so sorry, we've made you deaf tool.
Wonderful. We had Martin ask question about what equipment we use. Let me just go back to the question.
The equipment to use different parts of the machine.
Right.
The analysis, we use an ordinary sound level meter with octave bands. Third octaves are a waste of time. We use an octave band noise meter, and we use smartphones, and we also use analysis software, which is available from sound level meter manufacturers. We tend to record audio, then analyze it afterwards, and on site we may well use a phone app to say, oh, there's a big tone at that frequency, that's the problem. Oh, that, what's the gear mesh frequency, or what's the blade pass frequency of that fan? You ask the engineer there and then and find out what it is. So it's a question of it's an attitude thing about the way you look at a machine. You say, as an engineer, we always ask the maintenance fitters and maintenance engineers on a site who know how the machine works, and then you can work out why it's noisy.
We have a question about manual blenders. Do you have any example to reduce the noise from manual blending activity using air tools with noise above 85 decibels?
Air tools are a serious problem. It's very difficult to reduce the noise retrospectively unless it's air exhaust. You can silence the exhaust on air tools with a shroud, or you can pipe the exhaust away, depending on the type of tool. If you can't do that, I will give you a You Are Doomed certificate. All you can do is try and buy a quieter piece of kit. Same for hand-on vibration. There's not a lot you can do because the tool is so small, and it's also, there's just nothing much you can do about the design. We have helped tool manufacturers reduce the noise from their tools, but that has to be designed in. It's a very difficult one. You're pretty well stuck with wearing hearing protection with high noise hand tools.
Excellent. We have another question. Do you rate Odeon as a good software for noise reduction
I'm not
simulation?
familiar with Odeon.
Hmm.
Most software is, it depends. If it's, we use computational fluid dynamics for aerodynamic noise sources, for fans and things, to work out efficiency and flows and so on. But for mechanical stuff, it's far too complicated. I'm not quite sure what Odeon software does, so I can't really comment on it. We use our own frequency analysis software, but most of the meter manufacturers do have frequency analysis, narrowband frequency analysis software. One of the really, really depressing things is that one of my colleagues was an Institute of Acoustics conference a while ago, and someone was talking about narrowband frequency analysis, and she was giving a presentation, and she asked how many of you noise consultant members of Institute of Acoustics use narrowband frequency analysis. Out of over 100 people in the room, only 5 people put their hands up. And I just don't get it. You can do it for free on a phone. There's no excuse. It's awful. So it is a big problem, is knowledge within the acoustic community, because the money, follow the money. Most money in noise as a consultancy is based on measurement. A lot of, we have real problems recruiting because most people specializing in noise, if you're an occupational hygienist, you're not an engineer who can look at a machine and work out. Noise consultants are similar. Most of them aren't engineers. So it's quite, we have real trouble recruiting people who've got engineering capabilities as well as noise. It's rare. That's one of the reasons why the standard of noise control in noise risk assessment reports is so bad.
Some of you are leaving. Just want to let you know there's going to be another Peter will be offering another webinar on March 7. It's going to be at 7 a.m. UK time, so that participants from Australia and New Zealand and Malaysia and China can also attend.
If you want more information or got questions, you can always send them to me, and I'll get back to you with answers. If like if you can send me the details of the Odeon software, for example, William, so that I can then comment on it. Just send me an email and I'll get back to you.
Before we end the webinar, what we would like to do is, if you all can show your video, if you are able to, it may be, then what Rita will do is take a picture of a screenshot for everyone. Okay, so.
Well, posterity.
Yeah, I'm telling you, this is a very unique opportunity for everyone. Yeah, I can see some familiar faces. Wow, look at this. Okay, and very nice. All right, so let's see one more time. And Rita, you will be able to take the screenshot. Okay. All right. I don't see you, Rita.
Hi, everybody. So I've put on view,
Yeah.
but I only see people. Is there more? Large
There may be
gallery. Oh,
more.
here's a large gallery.
Okay.
Let me see if I can get some more faces. Oh, there you go. There you go. Right, so I'm quickly gonna do a screenshot. So if everybody can give me a huge big smile, look in front of you.
Say
1, 2,
cheese.
3. There you go. Thank you so much. I've got it.
All right. So, hey, everyone, thank you so much for attending, Peter. Thank you, as always. Remember to register for the Iowa 2024. Alison has given you the link, and we may be seeing you in Dublin. All right. Thanks, everyone. Please watch for the Iowa website and LinkedIn page.